Transistor. Transistor logic is a class of digital circuits built from bipolar junction transistors and resistors. It is called transistor. Transistor logic because both the logic gating function and the amplifying function are performed by transistors. TTL is notable for being a widespread integrated circuit family used in many applications such as computers, industrial controls, test equipment and instrumentation, consumer electronics, synthesizers, etc. The designation TTL is sometimes used to mean TTL-compatible logic levels, even when not associated directly with TTL integrated circuits, for example as a label on the inputs and outputs of electronic instruments. After their introduction in integrated circuit form in 1963 by Sylvania, TTL integrated circuits were manufactured by several semiconductor companies, with the 7400 series by Texas Instruments becoming particularly popular. TTL manufacturers offered a wide range of logic gate, flip-flops, counters, and other circuits. Several variations from the original bipolar TTL concept were developed, giving circuits with higher speed or lower power dissipation to allow optimization of a design. TTL circuit simplified design of systems compared to earlier logic families, offering superior speed to resistor. Transistor logic and easier design layout than emitter-coupled logic. The design of the input and outputs of TTL gates allowed many elements to be interconnected. TTL became the foundation of computers and other digital electronics. Even after much larger-scale integrated circuits made multiple circuit board processors obsolete, TTL devices still found extensive use as the glue logic interfacing more densely integrated components. TTL devices were originally made in ceramic and plastic dual-inline packages, and flat pack form. TTL chips are now also made in surface mount packages. Successors to the original bipolar TTL logic often are interchangeable in function with the original circuits, but with improved speed or lower power dissipation. History. TTL was invented in 1961 by James L. Buie of TRW, particularly suited to the newly developing integrated circuit design technology, and it was originally named transistor-coupled transistor logic. The first commercial integrated circuit TTL devices were manufactured by Sylvania in 1963, called the Sylvania Universal High-Level Logic Family. The Sylvania parts were used in the controls of the Phoenix missile. TTL became popular with electronic systems designers after Texas Instruments introduced the 5400 series of ICs, with military temperature range, in 1964 and the later 7400 series, specified over a narrower range, and with inexpensive plastic packages in 1966. The Texas Instruments 7400 family became an industry standard. Compatible parts were made by Motorola, AMD, Fairchild, Intel, Intersal, Signetics, Mullard, Siemens, SGS Thompson and National Semiconductor, and many other companies, even in the Eastern Bloc. Not only did others make compatible TTL parts, but compatible parts were made using many other circuit technologies as well. At least one manufacturer, IBM, produced non-compatible TTL circuits for its own use. IBM used the technology in the IBM System/38, IBM 4300, and IBM 3081. The term TTL is applied to many successive generations of bipolar logic, with gradual improvements in speed and power consumption over about 2 decades. The most recently introduced family, 74ASALS Advanced Schottky, was introduced in 1985. As of 2008, Texas Instruments continues to supply the more general-purpose chips in numerous obsolete technology families, albeit at increased prices. Typically, TTL chips integrate no more than a few hundred transistors each. Functions within a single package generally range from a few logic gates to a microprocessor bit slice. TTL also became important because its low cost made digital techniques economically practical for tasks previously done by analog methods. The CAN-BAC 1, ancestor to the first personal computers, used TTL for its CPU instead of a microprocessor chip, which was not available in 1971. The 1973 Xerox Alto and 1981 Star workstations, which introduced the graphical user interface, used TTL circuits integrated at the level of ALUs and bitslices, respectively. Most computers used TTL-compatible glue logic between larger chips well into the 1990s. Until the advent of programmable logic, discrete bipolar logic was used to prototype and emulate microarchitectures under development. Implementation: fundamental TTL gate. TTL inputs are the emitters of a multiple emitter transistor. This IC structure is functionally equivalent to multiple transistors where the bases and collectors are tied together. The output is buffered by a common emitter amplifier. Inputs both logical ones. When all the inputs are held at high voltage, the bipolar emitter junctions of the multiple emitter transistor are reverse biased. Unlike DTL, a smaller E collector or current is drawn by each of the inputs. This is because the transistor is in reverse active mode. An approximately constant current flows from the positive rail, through the resistor and into the base of the multiple emitter transistor. This current passes through the base emitter junction of the output transistor, allowing it to conduct and pulling the output voltage low. An input logical 0. Note that the base collector junction of the multiple emitter transistor and the base emitter junction of the output transistor are in series between the bottom of the resistor and ground. If one input voltage becomes 0, the corresponding base emitter junction of the multiple emitter transistor is in parallel with these two junctions. A phenomenon called current steering means that when two voltage-stable elements with different threshold voltages are connected in parallel, the current flows through the path with a smaller threshold voltage. As a result, no current flows through the base of the output transistor, causing it to stop conducting and the output voltage becomes high. During the transition, the input transistor is briefly in its active region. So it draws a large current away from the base of the output transistor and thus quickly discharges its base. This is a critical advantage of TTL over DTL that speeds up the transition over a diode input structure. The main disadvantage of TTL with a simple output stage is the relatively high output resistance at output logical 1 that is completely determined by the output collector resistor. It limits the number of inputs that can be connected. Some advantage of the simple output stage is the high voltage level of the output logical 1, when the output is not loaded. A common variation emits the collector resistor of the output transistor, making an open collector output. This allows the designer to fabricate logic by connecting the open collector outputs of several logic gates together and providing a single external pull-up resistor. If any of the logic gates becomes logic low, the combined output will be low. Examples of this type of gate are the 7401 and 7403 series. TTL with a totem pole output stage. To solve the problem with the high output resistance of the simple output stage, the second schematic adds to this a totem pole output. It consists of the two NPN transistors V3 and V4, the lifting diode V5 and the current limiting resistor R3. It is driven by applying the same current steering idea as above. When V2 is off, V4 is off as well and V3 operates an active region as a voltage follower producing high output voltage. When V2 is on, it activates V4, driving low voltage to the output. V2 and V4 collector emitter junctions connect V4 bipolar emitter junction in parallel to the series connected V3 bipolar emitter and V5 anode cathode junctions. V3 base current is deprived. The transistor turns off, and it does not impact on the output. In the middle of the transition, the resistor R3 limits the current flowing directly through the series-connected transistor V3, diode V5 and transistor V4 that are all conducting. It also limits the output current in the case of output logical 1, and short connection to the ground. The strength of the gate may be increased without proportionally affecting the power consumption by removing the pull-up and pull-down resistors from the output stage. The main advantage of TTL with a totem pole output stage is the low output resistance at output logical 1. It is determined by the upper output transistor V3 operating in active region as a voltage follower. The resistor R3 does not increase the output resistance since it is connected in the V3 collector and its influence is compensated by the negative feedback. A disadvantage of the totem pole output stage is the decreased voltage level of the output logical 1. The reason of this reduction are the voltage drops across the V3 basia emitter and V5 anodia cathode junctions. Interfacing considerations, like DTL, TTL is a current sinking logic since a current must be drawn from inputs to bring them to a logic 0 level. At low input voltage, the TTL input sources current which must be absorbed by the previous stage. The maximum value of this current is about 1.6 mA for a standard TTL gate. The input source has to be low resistive enough so that the flowing current creates only a negligible voltage drop across it, for the input to be considered as a logical 0. TTL inputs are sometimes simply left floating to provide a logical 1, though this usage is not recommended. Standard TTL circuits operate with a 5-volt power supply. A TTL input signal is defined as low, when between 0 of V and 0.8 of V with respect to the ground terminal, and high, when between 2.2 of V and 5 of V, and if a voltage signal ranges between 0.8 volts and 2 volts were to be sent into the input of a TTL gate, there would be no certain response from the gate and therefore it is considered uncertain. TTL outputs are typically restricted to narrower limits of between 0 of V and 0.4 of V for a low, and between 2.6 of V and 5 of V for a high, providing 0.4 V of noise immunity. Standardization of the TTL levels was so ubiquitous that complex circuit boards often contain TTL chips made by many different manufacturers selected for availability and cost, compatibility being assured. Two circuit board units off the same assembly line on different successive days or weeks might have a different mix of brands of chips in the same positions on the board. Repair was possible with chips manufactured years later than original components. Within usefully broad limits, logic gates could be treated as ideal Boolean devices without concern for electrical limitations. In some cases, the voltage level of the totem pole output stage at output logical 1 can be increased up to VCC by connecting an external resistor between the V3 collector and the positive rail. It pulls up the V5 cathode and cuts off the diode. However, this technique actually converts the sophisticated totem pole outputs into a simple output stage having significant output resistance when driving a high level. Packaging. Like most integrated circuits of the period 1965–1990, TTL devices are usually packaged in through-hole, dual inline packages with between 14 and 24 lead wires, usually made of epoxy plastic or sometimes of ceramic. Beam lead chip dies without packages were made for assembly into larger arrays as hybrid integrated circuits. Parts for military and aerospace applications were packaged in flat packs, a form of surface mount package, with leads suitable for welding or soldering to printed circuit boards. Today, many TTL-compatible devices are available in surface mount packages, which are available in a wider array of types than through-hole packages. TTL is particularly well suited to bipolar integrated circuits because additional inputs to a gate merely required additional emitters on a shared base region of the input transistor. If individually packaged transistors were used, the cost of all the transistors would discourage one from using such an input structure. But in an integrated circuit, the additional emitters for extra gate inputs add only a small area. Comparison with other logic families. TTL devices consume substantially more power than equivalent CMOS devices at rest, but power consumption does not increase with clock speed as rapidly as for CMOS devices. Compared to contemporary ECL circuits, TTL uses less power and has easier design rules but is substantially slower. Designers can combine ECL and TTL devices in the same system to achieve best overall performance and economy, but level-shifting devices are required between the two logic families. TTL is less sensitive to damage from electrostatic discharge than early CMOS devices. Due to the output structure of TTL devices, the output's impedance is asymmetrical between the high and low state, making them unsuitable for driving transmission lines. This drawback is usually overcome by buffering the outputs with special line driver devices where signals need to be sent through cables. ECL, by virtue of its symmetric low impedance output structure, does not have this drawback. The TTL totem pole output structure often has a momentary overlap when both the upper and lower transistors are conducting, resulting in a substantial pulse of current drawn from the power supply. These pulses can couple in unexpected ways between multiple integrated circuit packages, resulting in reduced noise margin and lower performance. TTL systems usually have a decoupling capacitor for every one or two IC packages, so that a current pulse from one TTL chip does not momentarily reduce the supply voltage to another. Several manufacturers now supply CMOS logic equivalents with TTL-compatible input and output levels, usually bearing part numbers similar to the equivalent TTL component and with the same pinouts. For example, the 74HC-T00 series provides many drop-in replacements for bipolar 7400 series parts, but uses CMOS technology. Subtypes, successive generations of technology produced compatible parts with improved power consumption or switching speed, or both. Although vendors uniformly marketed these various product lines as TTL with Schottky diodes, some of the underlying circuits, such as used in the RLS family, could rather be considered DTL. Variations of and successors to the basic TTL family, which has a typical gate propagation delay of 10 nanoseconds and a power dissipation of 10 MW per gate, for a power euro delay product or switching energy of about 100 pJ, include low-power TTL, which traded switching speed for a reduction in power consumption, high-speed TTL, with faster switching than standard TTL but significantly higher power dissipation, Schottky TTL, introduced in 1969, which used Schottky diode clamps at gate inputs to prevent charge storage and improve switching time. These gates operated more quickly but at higher power dissipation. Low-power Schottky TTL used the higher resistance values of low-power TTL in the Schottky diodes to provide a good combination of speed and reduced power consumption, and PDP of about 20 pJ. Probably the most common type of TTL, these were used as glue logic in microcomputers, essentially replacing the former H, L, and S subfamilies. Fast and advanced Schottky variants of LS from Fairchild and TI, respectively, circa 1985, with Miller-Killer circuits to speed up the low-to-high transition. These families achieved PDPs of 10 pJ and 4 pJ, respectively, the lowest of all the TTL families. Low-voltage TTL for 3.3-volt power supplies and memory interfacing. Most manufacturers offer commercial and extended temperature ranges. For example, Texas Instruments 7400 series parts are rated from 0 to 70 °C, and 5400 series devices over the military specification temperature range of a 55 to plus 125 °C. Special quality levels and high reliability parts are available for military and aerospace applications. Radiation-hardened devices are offered for space applications. Applications. Before the advent of VLSI devices, TTL integrated circuits were a standard method of construction for the processors of mini-computer and mainframe processors, such as the DEC VAX and Data General Eclipse, and for equipment such as machine tool numerical controls, printers and video display terminals. As microprocessors became more functional, TTL devices became important for glue logic applications, such as fast bus drivers on a motherboard, which tie together the function blocks realized in VLSI elements. Analog applications. While originally designed to handle logic-level digital signals, a TTL inverter can be biased as an analog amplifier. Connecting a resistor between the output and the input biases the TTL element as a negative feedback amplifier. Such amplifiers may be useful to convert analog signals to the digital domain but would not ordinarily be used where analog amplification is the primary purpose. TTL inverters can also be used in crystal oscillators where their analog amplification ability is significant. See also, positive emitter coupled logic, digital circuit, notes. References, Ayres, J. Oconee 215 Notes for Lecture 4. Harvard University Faculty Webpage. Archive of webpage from University of Connecticut. ND. Retrieved September 17, 2008. US 3,283,170, James L. Buey, Coupling Transistor Logic and Other Circuits, issued November 1, 1966, assigned to TRW Semiconductors, Incorporated. The Computer History Museum. 1963, Standard Logic Families introduced 2007. Retrieved April 16, 2008. Engineering Staff. The TTL Data Book for Design Engineers. First ed. Dallas, Texas Instruments. 1973. Aaron, H. Electronic Portable Instruments, Design and Applications. CRC Press. 2003. ISBN 0-8493-1998-6. Google Preview available. Fairchild Semiconductor. An Introduction to and Comparison of 74HC TTL Compatible CMOS Logic. 1984. Horowitz, P. and Winfield Hill, W. The Art of Electronics. Second ed. Cambridge University Press. 1989. ISBN 0-521-37095-7, Klein, Ekenbach 1. Vintage-computer.com 2008. Lancaster, DTTL Cookbook. Indianapolis, Howard W. Sams and Colorado, 1975. ISBN 0-672-21035-5. Millman, J. Microelectronics Digital and Analog Circuits and Systems. New York, McGraw-Hill Book Company 1979. ISBN 0-07-042327-X, Pittler, M.S., Powers, D.M., and Schnabel, D.L. System Development and Technology Aspects of the IBM 3081 Processor Complex. IBM Journal of Research and Development. 26, No. 1-11. Standard TTL Logic Levels ND. Twisted Pair Software. Thaler, DK Digital Logic Gates Part VASIC-world.com. 2006. Texas Instruments. Advanced Schottky Family. 1985. Retrieved September 17, 2008. Transistor Transistor Logic. SiliconFares.com. 2005. Retrieved September 17, 2008. Wobschall, D. Circuit Design for Electronic Instrumentation, Analog and Digital Devices from Sensor to Display 2D edition. New York, McGraw-Hill 1987. ISBN 0-07-071232-8, external links, Texas Instruments Logic Family Application Notes, TTL NAND and Gates from Lessons in Electric Circuits by Tony Kupfelt.